to Gradcast, the podcast and radio show of the Society of Graduate Students at Western University. I'm your host, Elizabeth Mohler.
And I'm your co-host, Gavin Tolometti.
And today we're here joined with Lindsay Grandy, who is a PhD student in the Department of Chemistry. Hi, Lindsay.
Hi, how are you guys doing?
Pretty good.
Yeah, pretty good for a Tuesday.
Yeah, to kick it off, just wondering if you can give us a little bit of an overview on what is the type of work that you are doing right now.
Yeah, so I study how copper corrodes in particular environments. So one of the most extreme environments that I study is under gamma radiation. So this work has a lot to do with and will be used to safely dispose of nuclear fuel.
So you get to see how well copper is able to withstand the radiation that nuclear waste gives off as it's stored?
Yeah, exactly. So we like to understand mechanistically how copper corrodes and at what rate, so we can accurately predict the behavior of the copper in long-term environments.
So how do you go about studying that, Lindsay?
So there are what we call a gamma cell. It's a particular instrument that gives off this high energy radiation. So we can mimic particular environments and then expose copper to radiation and then see how it acts. A lot of, if I can expand on that, also we use very high radiation, way higher than what that copper would be exposed to when we're actually disposing of nuclear waste. And then we try and sort of computationally model how that will affect the long-term corrosion. Because really the goal of what we're doing is understanding how the copper will corrode in very, very long times, hundreds to millions of years in the future. So it becomes a difficult task to do it experimentally, but the experiments are meant to back up computational models.
So how can the experimental work back up the computational models if you're trying to figure out how copper can withstand the radiation for a time span of 100 years?
Yeah, it's a really good question. So basically what we're trying to do, if we could all think back to first year chemistry, how we determine rates of reactions is by determining what elementary reaction is determining the overall reaction. So that's really the goal of the experimental work, is to determine what elementary reaction is determining the rate of the overall corrosion. It becomes a little bit complicated because at different time points and in different environments, different elementary reactions are affecting the overall rate. But that's what we're doing experimentally, is determining that elementary reaction.
And those results, because when you compare them to the computational model, so do you have to find a way to directly compare them, or do you have to let the models finish running before you can figure out whether the experimental results can be compared to them?
So what we would do is we would use a model and then compare it to experimental results to verify the accuracy of the model, and then we would expand it to long term. Does that answer that question?
Yeah, no, that makes a lot of sense. Because I'm guessing you can figure out, do you get to see at what point the copper would no longer be effective at that point?
Yeah, so really what we're trying to do is determine the thickness loss or the mass loss. So if I can digress a little bit actually and explain how nuclear waste is disposed of. So there's a canister in which we have the nuclear waste inside. That canister is made of carbon steel, so just a strong steel. And then that steel is coated with a layer of copper. So that layer of copper is meant to be the corrosion barrier for that nuclear waste that's within the canister. So we want to make sure that that thickness of copper is sufficient for containing the nuclear waste. So with these models and these rate equations and my experiments, we're trying to ensure that that copper doesn't corrode enough to let out the nuclear waste, if that makes sense.
And could you mentioned the term rate equation. Can you just kind of elaborate a little bit on what that is?
Yeah, so the rate equation would just be how fast the elementary reactions that are occurring, how fast they're going. So it's an analytical or a mathematical equation to describe the rate at a particular time.
Okay, that makes a lot of sense. Yeah, it's good for the listeners to get a good idea of what that would mean when it comes to figuring out how thick the copper layer would be.
Mm-hmm.
So this has never been studied before. So because I thought they've been storing nuclear waste for years now, and they've never checked to see how long the copper would be able to withstand the radiation before it's completely eroded.
So you're right, that we are storing nuclear waste right now, but the storage facilities, it's more of a temporary thing, how they're storing it right now. What I'm studying is Canada's plan for the permanent long-term disposal of nuclear waste.
So how do they store them right now if it's only temporary? Is it just put in the barrels and they're putting a chamber underground until they have to move them again?
They're currently actually, they're not underground. They're just in warehouses in these big concrete buildings, basically.
Okay, because I've always seen these like schematics of, I guess these must be the planned storage methods of they take these barrels, a good few hundred, maybe more. I might be getting the numbers a bit mixed up, like about a few hundred meters below the ground, so they can keep them away from getting leaking into the water table, the groundwater table, and contaminating rivers and probably water supplies to nearby settlements. But then it's the whole question, I guess, with what you're studying is, can we leave the barrels and the waste down there for hundreds of years without having to worry if they're going to be corrode through and leak?
Yeah, so what you're talking about is the permanent disposal plan. The plan currently is to use a deep geological repository. So it's basically like a big storage facility deep underground. It's actually 500 meters at least underground. So completely isolated from our groundwater and society just in general. And then there are multiple barriers. So the one that I'm studying is the copper layer, but there are actually many barriers that are in place, both natural and engineered, to completely isolate that waste and make sure that it's contained. Yeah.
So these barrels, how are they? I know we talked about this a little bit, but how are they stored and then disposed of in a way that's safe?
So because of the radiation?
Yeah.
Yeah. So currently we have a lot of robotics to try and handle the waste safely. And a lot of research is going into how we can do everything that needs to be done completely. Yeah, obviously not putting any humans in harm's way because of the radiation. Yeah.
And have you been able to get to see all this, the storage and the transferring of nuclear waste to different sites in person, or have you not had a chance to go out there and see how the whole process works?
Yeah, I've been very lucky in that I have been able to see at many stages the storage facilities and the nuclear waste management organization. So that's the people that are in charge of the nuclear waste. I've been able to discuss a lot with them and go to their facilities, see mock-ups of the DGR and the container, and all aspects related to the nuclear waste disposal. There are a lot of projects as well that are going into safely storing the nuclear fuel, both now and in the future for the permanent disposal. So I've been able to also talk to and sometimes collaborate with other chemists and scientists who are studying different aspects of the overall disposal project.
And in terms of the permanent disposal of these barrels, could you kind of just expand a little bit more on that?
Yep, so the permanent disposal, of course, we need a way to store the nuclear waste that has been used currently. So as I was sort of explaining before, Canada's current plan is to use the Deep Geological Repository to permanently dispose of the waste. Yeah, the use of a DGR, a Deep Geological Repository, most countries agree that this is the best way to permanently dispose of this nuclear waste, because it really is, you know, a worldwide problem, or, you know, something that is a lot of countries are trying to address. So there has been a lot of research into the best way to do that. Canada has particular plans related to, you know, the site of the Deep Geological Repository. A lot goes into the site because of the particular rock. So the igneous, or forget the other type of rock. That's not exactly my my area.
There's sedimentary and there's metamorphic.
Yeah, right. Maybe it's sedimentary. Shouldn't quote me on that, but yeah, so a lot of research goes into the type of rock that they're going to put the deep geological repository in. There's also around the container there will be a clay box, so it's a bentonite clay box, and the purpose of that is if it's ever exposed to water, the clay will swell, and that will provide additional protection to the waste within. And then, of course, there's the copper layer, which is important for the corrosion barrier. And there are other, how Canada produces nuclear fuel. Even the nuclear uranium pellets themselves are a way to keep the fuel contained, because it's a solid pellet. Which means that it's not as equally or as easily, I don't know, released. So.
And the corrosion barrier is what?
That's the copper layer of the container.
Gotcha.
Yeah.
Okay. It's interesting that you mentioned the clay minerals being one additional protective layer for storing the nuclear radiation, nuclear waste. Because I'm in the geology department, and I've occasionally heard how clay minerals are being studied more to see how they can be more efficient in being used to collect toxic elements that get caught in water, and to also be used as insulating and protective layers to stop nuclear waste from being leached into the environment. And a moment ago, you mentioned that you've sometimes had a chance to chat and collaborate with other scientists working on these types of issues. Have you been able to collaborate with you said other chemists, but have you been able to collaborate with other scientists?
Yeah, not necessarily collaborate, but definitely there's a lot of different type of scientists that are researching the same general problem, or, you know, with the same goal in mind. So there are definitely geologists studying the rock, and microbiologists as well within the clay. Yeah, and engineers, a lot of types of scientists, yeah.
Okay, because it's always good when you hear that with grad students getting to collaborate, even not collaborate, but yet even just get to chat with other scientists studying similar topics in their field, because it gives you a good perspective of the bigger and smaller problems that are trying to be solved, especially when it comes to nuclear waste, because I know it's a very controversial energy topic because it produces a lot of energy and it's cleaner than oil and gas and other fossil fuels, but it still has this long-lasting issue of where do we put the material that's produced from it. Does this conversation come up a lot when people approach your lab or people approach you about your research?
It has definitely been a conversation that I've had to have a couple times. It's usually more with friends or family and less with scientists, but it's definitely something that the NWMO and like my PI and other professors have had to address. I think that part of the NWMO is the organization, I'll just remind you, that is dealing with the disposal of nuclear waste. They do a lot of work to try and educate the community, and particularly the community that the site is going to be in the future, the Deep Geological Repository. They do a lot to try and educate the general community about how we're planning on making sure everything's safe, because there is a lot of, fear that comes along with just the word radiation or nuclear. But there's a lot of science that is behind everything that we do. And it's important to just educate everyone on that particular thing. Yeah.
You mentioned educating the community. Like, what sorts of things have been done to educate the community around the safety of nuclear waste?
I know they do a lot of outreach, particularly for people or like children, really, who are interested in science. They have sort of STEM programs where they go and give talks and try and educate the next generation. But they also hold community meetings where, like, town halls where people can come and ask questions directly to the scientists who are working on this, on these problems. So science communication definitely is a large part of what we do.
And have you been able to get quite involved in the public engagement and science communication with these communities?
Here and there. I'm less of an expert, I think, than my professor and other people, but I certainly try and engage with just general conversations, even like this one, and just make sure that people know that it's not just we're just dumping a bunch of nuclear waste in the ground. We have an actual plan that is based around hard science.
I'm guessing you must get this question a lot, or correct me if I'm wrong, let me know. But when you tell them, oh, I'm trying to figure out if the layer of copper is able to see how long it can withstand the nuclear waste radiation, are you able to say that what companies are currently using now is sufficient, or are you saying that more work is required to figure this out?
Yeah, so I mean, even the way you just phrased it, and it's no fault of your own, but I generally don't phrase it like that. It's not that I'm trying to, make sure this thickness of copper safely contains it. What we're trying to do is make sure, we have a reasonable maximum corrosion limit, so we know that the amount of copper that we're planning on using, but the NWMO is planning on using, we know that it'll be fine. We know that. We just, more and more research is being done to make sure to, prove to people and prove to ourselves that, we know exactly how much of that copper will corrode.
So it's not really about how thick it is, it's about sort of how much and how fast the copper is going to corrode in these barrels. Is that kind of close?
Yeah. So what is the thickness of that copper layer that will corrode, I guess.
Gotcha.
Okay. Okay, that makes a lot of sense. All right. Now I feel a little bit silly for the question I asked earlier.
No, it's okay.
We've all done it. So Lindsay, where are you sort of thinking you'd like to go next with your research? You've kind of shared with us where you're at now. What are your plans in terms of what you'd like to do moving forward?
Career-wise?
Yeah.
Yeah, well, I'm quite passionate about what I do. And I think nuclear waste or nuclear energy is at least a part of our future. But I am sort of planning on switching gears after my PhD and going more into teaching at a university level, mostly because I just love talking about chemistry. So, yeah.
Does that mean there's probably a postdoc in your future or maybe a slightly different route?
Yeah, so definitely postdoc is on the table, and that's only if I don't get a job. I'm currently actually applying for teaching jobs to see where that goes, but yeah, a postdoc is a close second choice. I mean,
is there something that we know that we're in this sort of pandemic world? Are you able to sort of keep up with your research and do your research in the same way that maybe you would have pre-pandemic?
It's definitely a lot harder. A lot of all of my, research is based on being able to get into the lab and do experimental work. So when the school shut down, and since then, experimental research is significantly slowed. So that's definitely made it harder to continue my research. But we're lucky enough, I think, that we're able to go into the lab a little bit. So I'm able to get experimental work done, just not as much as pre-pandemic, that's for sure.
What about the computational modeling? Are you able to do that at home, or does it still require specific programs that that are only available on campus and in the lab?
Yeah, no, definitely I've been able to do that at home. The computational model I'm trying to contribute to, but it falls a lot more on, we have a postdoc in our lab. He does a lot more modeling, and I think that the grad students that come after me will probably do more modeling than I. I'm definitely more of an experimental chemist, but I have been doing a lot more modeling since the pandemic because, yeah, it is accessible from home. So I've been lucky in that way as well, for sure.
Do you need to use a special software to do that kind of computer modeling?
Yep, so I use the software ComSol Multiphysics. So that allows you to input, like we were talking about, rate equations and chemical reactions and things like that, and then, yeah, model in that way.
Okay, that's pretty cool. Yeah, it's always interesting to hear about all these different softwares to do different types of computer modeling in sciences and see what problems they can help solve. So I definitely have to ask, what is it that brought you into studying nuclear waste and nuclear energy? What is it about this field that fascinated you so much?
Yeah, so I think there's sort of two answers. My first and possibly more boring answer is that I just think the chemistry is interesting. I think radiation chemistry is sort of niche, and gamma radiation or ionizing radiation, the type that I study right now, is not generally encountered on a day-to-day. So I just find that type of chemistry interesting. But nuclear energy in general, I think, I like to think of myself as, somewhat of an environmentalist. I think that nuclear energy is clean and really important in our future if we're wanting to have a better environmentally, better ways of getting energy in the future. So I think that this research really contributes to, the end goal is really positive for me. So when I, was thinking about grad school and I came across this project, certainly that really attracted me, that the overall goal is something that's, positive and contributes to society in such a positive way.
No,
Very timely.
Yeah,
Very
no, that is.
Sorry, pardon?
I just said very timely and very relevant. This is a
Yeah.
hot button issue in the news, certainly with climate change, conversations happening. So yeah, very timely and relevant for sure.
Yeah, and I've talked to a lot of, my colleagues who are also studying nuclear energy in general, at conferences and stuff. And I find that that's a lot of the reason that most people are there, is that this is at least a part of our future. And yeah, what better way to contribute to society than studying nuclear energy. Yeah.
No, it is very good. And so, Lindsay, unfortunately, we are running out of time, getting close to the end of our episode. But before we go, is there any social media handle or lab website you'd like to shout out for the audience?
Yeah, so if you're interested in learning more about what my lab does, our lab group name is Radiation Assisted Materials Performance Science. So our group is called RAMPS. More information about what we do is at our group website, rampsgroup.org, or you can find me on Twitter at Dr. Linds, DRLINDS.
Great. Thank you so much, Lindsay. It's been a pleasure to talk with you today.
Yeah.
You've been listening to Gradcast, the podcast and radio show of the Society of Graduate Students at Western University. I've been your host, Elizabeth Mohler, and joined by my co-host, Gavin Tolometti. And we've been speaking today with Lindsay Grandy. If you want to listen to this episode, you can find us on YouTube. You can also find us at Gradcast Radio at 94.9 FM. If you want to get in contact with us, you can look us up on Twitter or email us at gradcastradio@gmail.com. Thanks for listening and have a great night.